read it. In addition, 6.6. Next week's lab is physical properties of water. Make sure that your pre-lab material is complete, meaning a procedure sufficient to conduct the experiment, along with answers to your pre-lab assignment questions. As usual, I did open up next week's module, and we can see down here that there is a page for the lab. We're not changing anything, so all that page really does is remind you about 5 things you have to have done before going. But I just put up a heating and cooling curve video. It did take me a little while to get closed captioning done. I would have told you on Wednesday. I wasn't sure if I was going to get it done on time for lecture day. Because we're not going to get to that. It's in the lecture but we're not going to get there before lab. I'm a little behind. So this way you'll have it to watch and take notes of. It's the same slides as the usual slides, so it has the page numbers up in the corner. That way you'll be prepared for the lab. You have to do the similar types of calculations for the lab. And I didn't want to wait until, we just teach it next week, Wednesday maybe, and half of you are already done with the lab. That would have been fair. So this way it's already up there. Everybody had a chance to look at it over the weekend, or at least before your lab, and that way you'll take understated calculations a little bit easier. In addition, we had a PhD this morning, and you know that the lab is going to be slightly ahead of lecture material. It's going to be slightly ahead of lecture material for the students earlier in the week. So therefore, their pre-lab talks might be a little longer, just to make sure you're comfortable with the types of calculations you'll have to do. Any questions about that? So I just want to make sure you're aware that that was there. As usual, when we get out of this, so I don't forget. We know we have a quiz today. Why are you scrolling? We know we have a quiz today, last 20 minutes. As far as exam 3, we know it's Thursday the 20th, 5:30 p.m., 60 minutes, and the LAPM for most students. Again, we've talked a couple times, it'll be somewhere in chapter 8, usually at the end of periodic trends, in case you want to look advanced. Assigned problems, I have a couple from page 211, and we do have a final list for Moodle Exam 2 homework problems, unless for some reason I don't get to a certain point I need to get to today, in which case you'll be given a canvas announcement with, I think it's number 99 and 96. I'm unsure if I'm going to get to that material. I think I will, but it depends on the questions. So in which case we'll truncate it. I'm not going to have you do a question because we haven't covered the material for it. Are there any questions in general? Good? Okay. So we're starting on page 204. Yes, the slide is blank because we're doing some review. Just to make sure we're remembering what we did on Wednesday. So number 1 asks again, what is heat? It's kind of how we started on Wednesday, or somewhere on Wednesday as well. Transfer of thermal energy. We're thinking about our energy being transferred between our system and our surroundings. Recall that heat is extensive. It does depend on the amount. It has to be really crucial for these next 2 sections. If we have different amounts, we're going to have different amounts of heat, and you'll have to take that into consideration in your calculations. As a review, a state function is a property of the system that is independent of path. Remember, I gave a scenario of some acid in a graduate cylinder, and also you come back and half is gone. So you don't need to know what really happened. You just need to be able to take 2 numbers and subtract them from each other. So if we have a state function, the change in that property or that variable is simply the final minus the initial. Heat, unless we know the path, is not a state function because we have 2 different paths, and we saw that with our 2 different types of calendars last time. Any questions before we now define heat as a state function? Enthalpy is the heat content of a reaction or a quantity to describe the heat flow into or out of the system in a process that occurs at constant pressure. So if we know that we have constant pressure, then we have enthalpy. So if we have this, we have enthalpy. Variable for that is H. Again, we don't know the exact amount of enthalpy. Think of all the places we could be getting our thermal energy from within a system. So we look at the change in the enthalpy. Therefore, if we're thinking about our change in enthalpy, this is just simply heat under constant pressure. The subscript P is just telling us we have constant pressure conditions. So it's still heat, and all the things we talked about with heat still apply. products, an initial stage of the reaction are the reactants. So instead of F and I, we use P and R. Change in enthalpy would simply be equal to the change in the enthalpy for the products minus the change in the enthalpy for the reactants. Now I'm putting those deltas in front of the H's, whereas before they weren't in front of the X's. Some variables you can measure precisely, right? The change in volume, you have initial and final. This is about heat content or thermal energy, and it's, as we discussed, really impossible to know the exact amount. So we're thinking about changes when we have a variable that we don't know the exact amount for. It's still intensive, it's still heat. Therefore, if you run one reaction twice with different amounts of, let's say, reactants, you're going to have different amounts of heat transfer. How can we visualize this? We're actually going to have a image coming up in a little bit that will make it easier to visualize this. Right now for you, I know it's hard to visualize heat transfer, but think about what's going on in the reaction. Breaking bonds, making bonds, you have collisions between particles, transferring your thermal energy, so you can think about that when we started with our heat, the peach particle hitting the surface, the blue particle coming, and there's a transfer of energy because we saw the arrows change length. You want to use that to kind of visualize things. We also can try to visualize this with an energy diagram. We are going to be looking at that as well on the next page. As far as how do we calculate this, there are two different ways. We can do an experiment. Get a calorimeter up, and you can watch the temperature change, and use like Q equals MS delta T to calculate our enthalpy. Remember, enthalpy is just heat, so the same equation still works. Indirect ways is what 6.6 is all about. And those are the questions I had to exclude from the Blue Exam 2 homework, because we won't get to that today. So indirect, we can calculate using tabulated values from your textbook, or we can use known reaction enthalpies, things that you can measure directly to calorimeter, and then use those to figure out an unknown reaction. Again, something that we'll be practicing on Monday. Good? We're going to review. It's not marked review, number 4, or number 5 on the next page. However, enthalpy is just heat. So things like endothermic and exothermic still mean the same things. Yes, there's a lot there. More than this on your sheet. You have things to fill in. But if we have an endothermic system, we know heat is going into our system. Well, we have a reaction here, a process. We're melting ice. Our ice, water solid, has low enthalpy, where our y-axis is that arrow, that vertical arrow. We have to go up in enthalpy to get the liquid, which means we have to put energy into the system. You add heat for endothermic, well, you add enthalpy for endothermic, because enthalpy is simply heat. Meaning our energy diagram looks the same as it did before. We're putting energy in, the energy or enthalpy of the products is going to be at a higher level than the reactants. And of course, we do have that energy barrier all the time because we need to make bonds, break bonds, and make bonds, and have collisions, so there's always an input of energy. The newer things are the H part. So your delta H space is 0, greater than 0, because Q is greater than 0. And therefore, the final enthalpy is greater than the initial enthalpy, or the product enthalpy is greater than the reactant enthalpy. At the bottom of the slide, we are showing that we could describe this in words. So 6.01 kilojoules are absorbed for every 1 mole of ice that melts at 0 degrees Celsius at 1 ATM. Again, enthalpy is extensive, so if we had 2 moles of ice, it'd be twice as much that we need. We need 12.02 kilojoules then. We also can put this in symbolic form. H2O solid going to H2O liquid has an enthalpy of 6.01 kilojoules per mole. That's per mole of the reaction as written, meaning 1 mole of ice going to 1 mole of liquid. What I have typed at the bottom of the slide is also called a thermochemical equation. It's not just a chemical equation, it also has the thermodynamic information, the enthalpy there. And although we need to put in that enthalpy, it always goes behind when you're writing it. We know if we're putting it in because it's a positive value. We have to add it. Are there any questions before I have to click to give you another example? There's another example. We take ammonium nitrate. We know it's soluble. We put it in some water. We get ammonium cations, aqueous, and nitrate anions, aqueous. Well, that process requires energy. It requires 25.4 kilojoules per mole of our ammonium nitrate. Meaning, if you dissolve ammonium nitrate in water and you put your hands around the beaker, it'll feel cold because it's sucking energy from the surroundings. Any questions? Good. Lots of people writing, so I'm trying to solve. We're going to go through the exothermic, which is on the next page at the top. Again, it's still exothermic. Heat is leaving the system. Well, now we just call the heat enthalpy because we know it's under constant pressure conditions. Again, a lot just came in with one click. Our enthalpy is going to be less than 0. Our Q is less than 0. That means the enthalpy for the reactants has to be greater than the enthalpy for the products because we're losing energy to the surroundings. Our reaction from our textbook image, we have high enthalpy for our reactants, CH4 and O2. When they react to form the carbon dioxide in the water, the enthalpy value is going down because there's energy leaving the system. You have that horizontal arrow going out. So heat is given off by the system to the surroundings. Our value for this enthalpy for this particular reaction is negative 890.4 kilojoules per mole the reaction is written, meaning it's for 1 mole of our methane or 2 moles of our oxygen. Notice the words. 890.4 kilojoules. There's no negative, because the negative is given to you by the word released. So we don't have the negative there, we have a word that tells you negative. For every 1 mole of methane that's combusted at 25 degrees Celsius and 1 atm. And again at the bottom, symbolic view, we have the chemical equation and the enthalpy information, meaning this is a thermochemical equation. And yes, the enthalpy information always is put afterwards. Don't let it overcomplicate your head. Enthalpy is just heat. We just know we have constant pressure. For our extra example is one that I actually had mentioned the other day. When you did your titration, you might have felt your flask of your beaker getting warm, and that's because an acid-base neutralization reaction is exothermic. So if we have 1 mole of HCl reacting with 1 mole of sodium hydroxide, we'll actually release 57.9 kilojoules of heat. Now, if you have less than a mole, it's going to be less heat. If you have more than a mole of each, then it's going to be more heat, because enthalpy is extensive. Good? Just trying to translate in your brain that this is the same thing. It's just heat. It's got a different name. And this is what I meant earlier when I said to help you visualize this. I said we can try to use an energy diagram to help us visualize this. This goes along with number 6. To go from our CH4 and our 2 O2s to get to our carbon dioxide and 2 waters, we of course need to break bonds, reorganize the atoms. To break all those bonds is that initial big energy input, which is why there's always a hill between the reactants and the products. It's only exothermic because in the end, the energy content of the product is simply less than what the reactants were. And therefore, that extra energy has to be released from the system. We have to conserve our energy. Any questions? We're going to go back to a couple equations. We used them the other day. I think it's Monday, the boring day. Remember we had our different equations for the first law of thermodynamics. We're going to use that one to help us understand the connection between enthalpy and internal energy. Before that, number 7, how are enthalpy and heat related? Remember, the amount of internal energy transfer. The difference is work. Can't spell this today. Meaning, if you have a reaction that's really not doing much work, precipitation reactions, not all redox, but some acid-base reactions are generally not doing work, meaning they're not pushing against the surroundings and stuff like that, then your measure for your enthalpy is telling you the change in internal energy. Just trying to help you see where we started, basically, with that internal energy idea. Good? Due to our chemical education research, this department, number 9, number 10, got put into electroactivity book about 10 years ago. And the reason is we saw that students were getting misconceptions from the examples that authors use. Next semester, there's another whole chapter on thermodynamics, and the main big idea is how do we know if a reaction will occur? We know the activity series, we know other things, but what is the fundamental reason why the reaction will occur or be spontaneous? Now for number 9, are all reactions that are exothermic spontaneous, meaning will happen? No, not all. Okay? One example I like to use is liquid water freezing. Oh my gosh, I was trying to put a triangle in. Too many triangles these days. Meaning going to solid water. That does not always occur. However, the change in enthalpy for this process is negative 6.01 kilojoules per mole. It's exothermic, but it does not always occur. However, textbook authors like to, maybe by chance or by not even thinking about it, use exothermic reactions as examples of reactions that do occur. We don't have all of our liquid water freezing. It has to be at the right temperature, right? So it doesn't always happen. What happens to the surroundings when a reaction is exothermic? They get warmer, right? They gain heat. As far as the same misconception shows up for things that are not spontaneous. Are all reactions that are endothermic not spontaneous, meaning will not happen? No. For those who like the winter sports, thankfully, some of the ice does stay, right? It doesn't all melt. It does at the right temperature. But we never have snow. So that's endothermic, and yes, it can happen. Or it might not happen. It depends on the temperature. So there's more than just enthalpy involved, which is why there's another whole chapter in the next semester of the course. What happens to surroundings when the reaction is endothermic? They get cooler. Any questions? We have some rules coming up for how to deal with chemical reactions when we're thinking about enthalpy. I forgot to click that. Sorry. There we go. When we're writing a thermochemical equation, this is 11.1, page 208 in case you got lost. As we've already seen, we need both the chemical equation and the enthalpy information. This is just one page that will kind of have everything in one place for you. We have already covered that. So you need both balanced equation and the enthalpy in order to have thermochemical. And notice, doesn't matter if it's endothermic or exothermic, because it's the same two examples from before, it always goes behind. What happened here? All I did is I reversed that reaction, right? What happened to the enthalpy? The value stayed the same because the change is equal to the products minus the reactants. If I flip things around, what were the products are now the reactants, and what were the reactants are now the products. Meaning, if you change the direction of a reaction, you simply change the sign on the value of the enthalpy. The number is the same. Because all you're doing is flipping how you subtract. We know enthalpy is extensive. We kind of mentioned it a couple times that if we had more or less, there'd be more or less heat exchange. Well, if I wrote a reaction with different balance, and there are times you have to do this, you'll see that on Monday, then we would of course have to change the enthalpy that's associated with that reaction. Which means write those as ratios, right? From this one right here, this would be negative 6.01 kilojoules for every 1 mole of liquid water. Maybe we've used those conversion factors. So you have to know what the balance is for your reaction in order to use your enthalpy correctly. And enthalpy is a state property or a state function, right? Which means there's more than one way we can calculate it because it's independent of path. We know it's constant pressure path, but it's also independent of the path we take to calculate. Which is why in section 6.6, there are 2 different ways to calculate, besides doing an actual experiment. So since enthalpy is a state function, there are many ways to calculate enthalpy and get the same answers. One thing we'll be doing in 6.6 is for the same reaction, using the 2 methods, and we're going to get the same answer. Any questions? Number 12 seems a little displaced, even for my brain. You're doing rules and also they ask about standard conditions. In chapter 5, for gases, we had STP being 0 degrees Celsius and 1 ATM. That's not the same for the thermodynamic community. We like a more reasonable temperature. Standard conditions in thermodynamics is 25 degrees Celsius and 1 ATM, the world we live in. The gas people just like to be cold, I guess. It's not that often when you're doing thermodynamic work that you're actually using the numbers, but you could be asked what standard conditions are. Next semester, you might use the numbers more. Any questions? I know it's quiz day to be really quiet. One more thing I have to get done, so I don't have to exclude any numbers from that list. We have in page 209, a big table with definitions for different types of reactions. We will not get through the table, but we'll get far enough. The first one is called enthalpy of formation. Think about this definition carefully because this one really troubles students' brains. First off, the variable is change in H, but the subscript is an F for formation. The enthalpy change associated with the production of 1 mole of the substance from its elements in their standard states. Meaning you restrict it in your balance. You have to have 1 product. Which means, as the examples on the screen show, you will at times have ratios. So if I was asked for the sum of the stoichiometric coefficients for either one of these, well, there's a 1 for the H2, there's a 1 for the H2, and there's a half, so it would be 2.5. The 2 little questions I don't have to exclude, it's just adding up the numbers. But making sure that you are having balance for 1 mole of your product. You won't always get ratios, but at times you do. Notice how the values are different depending on the state of the substance, too. Liquid versus solid, for the water, has different values. The enthalpy of formation for all elements in their standard state is 0, and the reason is it comes to the definition. If I wanted to make an element in the standard state, I have to use the element in their standard state. Meaning whatever the absolute enthalpy content of the reactant is, it's the same as the product. I happen to use diatomic oxygen for this example. It has to be standard state, meaning monoatomic oxygen would not be 0. Only diatomic. So if you peruse Appendix 2 of your textbook that has all kinds of enthalpies of formation in there, you'll notice a lot of zeros. And if you look over to see what it is, oh, it's an element in a standard state. Meaning, is it supposed to be a solid at 25 degrees Celsius? Is it supposed to be a liquid? Is it supposed to be a gas? Is it supposed to be diatomic or not? Things like that. Any questions? Next time we'll continue. It's quiz time. Maybe I've made a difference, but there are 2 things I wrote on a list about enthalpy of formation. Okay? The rest of